Hello, ALIFE2023. My name's Dr. Stuart Bartlett. I'm a staff scientist at California Institute of Technology. Thank you very much for inviting me to give a presentation about this paper that we published, only just last year. I'm very sad that I can't be with you in person up there in Sapporo. It would have been lovely to be able to come, but unfortunately my travel schedule just didn't allow me to make it. So I'm very sorry I can't be with you, and I want to say hi to all of you amazing people that I wish I could talk with and listen to your presentations. And I'm going to obviously follow the conference as closely as I can from here in California. I'm going to record my talk today since I'm scheduled to talk at a time which is 1:50 a.m. Pacific time. So I think my attentiveness might be better if I record it for you now. And please feel free to contact me afterwards if you have any questions or inquiries about this work. So yeah, without further ado, let's dig into the details of this paper, which is titled Computation by Convective Logic Gates and Thermal Communication. So this is work that followed on from several other studies. It is basically related to the nonlinear features that you get in convective fluid systems. Broadly speaking, convective fluid systems are fluid systems which have a temperature gradient across them, and that gives rise to a variety of interesting phenomena. The primary one is buoyancy-driven fluid flows, as demonstrated here in this beautiful diagram. The nonlinearity applies both to the growth of the plumes and also to the steady-state statistical behavior of these systems. So if these convective systems are driven very weakly, they will exhibit no convection. They will just move heat through themselves by diffusion. And obviously, you can't do any computation with a purely linear system. In this talk, we'll be dealing with laminar convective systems. So the basic properties of convective fluid systems are that they have this temperature gradient, and typically for the types of theoretical studies like this one, you deal with single-phase fluids, so Newtonian fluids, not complex fluids with too many things dissolved in them, or granular materials or anything like that. So we're dealing with a single-phase fluid, such as water, for example. It's a 2D system. We assume that there are two plates forming the upper and lower boundaries. One of them typically is heated to a high temperature, and the other is cooled to a lower temperature. Heat flows through the system by diffusion and convection, and so the system is free to choose this heat flux variable Q, since the two temperatures across the system are fixed. In this system has periodic boundary conditions, but in the rest of the talk, we'll be dealing with systems that have no slip walls on all four boundaries. So that means there's no fluid flow actually on the boundary. They're frictional walls. And we assume the Boussinesq approximation, which basically just states that any density differences caused by temperature gradients only influence the buoyancy force, but we're basically just assuming that it's still an incompressible fluid. And so in general, these systems have nonlinear responses. And so a natural question to ask is whether they can exhibit memory and computation. And of course, the reason I'm talking to you today is because they can. And this is something that we explored some years earlier in these previous publications. So the first one back in 2019 was all about basically exploring the entropy production of convecting systems, and in particular by trying to compare convective systems to heat engines. And the way we tried to explore this is we put momentum sinks in these convective flows. It's like putting a wind turbine in there, basically. And what we found is, due to what's known as the Coanda effect, convection plumes actually align themselves with obstacles due to the sort of the asymmetry of moving one way or another. And it turns out that you can configure those convective systems with multiple momentum sinks, and they will show bistability or multi-stability, and even a memory of their past states. You can actually get them to exhibit hysteresis loops. And then we thought, well, if we've got memory and hysteresis, then we should be able to carry out computation. So this follow-up study in the Royal Proceedings of the Royal Society A actually explored some very simple logic gates with a view to building circuits out of convective systems that are exposed to momentum sinks. And the idea we had was that the momentum extracted at these points in the flow could be communicated into these convective logic circuits. But in the end, it proved a little bit difficult to find a sensible way to be sort of extracting momentum and, you know, transporting it via circuits to other logic gates. So we eventually moved on to this alternative system where the information is not carried by a mechanical force or momentum, but by heat instead, which is a bit closer to what we're familiar with, which is wires. So that was the sort of inspiration behind the following project. For those of you who might be interested in the mathematical details, these are the equations of motion underlying our system. Continuity equation essentially says that the fluid is incompressible, so it's the flow lines are non-diverging overall. The momentum equation just tells us how momentum is conserved. Momentum diffuses, it changes according to pressure gradients, and it also changes according to temperature gradients, which is shown in that final buoyancy term there at the end of the second equation. There's also the advection diffusion equation, which describes how passive scalars are moved around the flow. In this case, how temperature is moved by the flow, represented by the vector v, and it also diffuses with a coefficient, with a thermal diffusivity chi there. And if you de-dimensionalize these equations, you can arrive at this version of the momentum equation, which is written only in terms of the dimensionless groups PR, or the Prandtl number, which is a ratio of the viscosity to the thermal diffusivity, and then also this other dimensionless group called the Rayleigh number, which is a dimensionless parameterization of the thermal driving force. So basically, if your flow has, you can come up with any configuration of the parameters you like, but if your flow has the same Prandtl and Rayleigh numbers, then it will show identical properties, basically. So when we simulate these kinds of systems or look at them in the laboratory, we typically see this kind of flow field. In the laminar regime, we basically have these what are called convection rolls and these plumes. The fluid is heated and it's rising in these plumes, and then it reaches the top boundary and it turns over, and then as it cools down and then drops to the other side. So these convection plumes, they typically take on their horizontal size is typically the same as the vertical dimension of the system. Of course, when you move into higher Rayleigh numbers and turbulent flows, the flow becomes more complex and you have smaller vortices, but we're only dealing with laminar flows in this work. So we basically wanted to try and exploit the nonlinearity and the multi-stability of these convective systems to try and do computation. And in particular, what we did is we took a system, and instead of having an integer aspect ratio of 2:1, for example, or 1:1, we used a non-integer aspect ratio. So what we actually did is used an aspect ratio of 1.5, because in that system, when you are in the laminar regime, the system is bistable because it could either take up a 2 convection cell state, as is shown here, or it can take up a single convection cell state where it has the single convection roll. So we're using this bistability, the fact that you can have either 2 or 1 convection rolls, essentially as our output for the computation. So that's basically our binary variable. So we have this 1.5 horizontal to 1 vertical aspect ratio, and what we do is we heat the system in this narrow region, the lower 1/9 of the system, where the temperature is held high at that point. And what we do is we define these convective logic gates such that their output is that small black region in the center. And of course, it took a little bit of engineering to make this system work. It took quite some tuning. Although, I mean, I didn't use an evolutionary algorithm. I probably should. In future work, maybe we should do that. the inputs to these convective logic gates are shown in the two red squares there. So input A and input B, left, right there. And basically with this system, what happens is, depending on the inputs, and inputs mean applying a temperature of approximately 0.5 or dimensionless temperature of 0.5 to those red regions. Depending on the input, you get different steady state flows, either the two convection cell state or the single convection cell state. In this case, the two inputs are off, so we're not applying any heat to those two little red squares. And of course, we have this convection plume in the center forming two convection cells. Now, the temperature in that black region, which is the output, is of course relatively high, or it's a dimensionless temperature of roughly 0.5. So it's somewhere in between the two extremes. So now we can ask, well, what happens if we apply an input to those two red regions? And so in this example, it looks like both of them are switched on. I can assure you is just one. And in fact, so with the input on the right there switched on, there's a dimensionless temperature of 0.5 maintained in that little red square there. And of course, what that does is it diverts the primary convection plume over to the left and flips the system into this single convection cell state. And what that means is that the temperature of the black output region there is relatively low. It's gone down to something like 0.2 or so. We can also switch on the input on the left instead, and you see there is a slight difference in the flow field there between the two. So if we switch on that leftmost input, we also go to this single convection cell state because the plume is sort of diverted over to the left. And again, the output region has a relatively low temperature. And then finally, if we apply both inputs, of course, we're still stuck in this single convection cell state because both of those inputs are dragging the convection plume over to make this clockwise rotation. And the output is, again, relatively low. The temperature of the output region is relatively low. So putting this all together, what we find is that we can actually make a NOR gate out of all these interactions on our convective logic gate here. So when we had that low input on both A and B, I'll just go back to it quickly. We had this high temperature in the output region. In fact, it's 0.53 there. And we basically threshold the output temperature and use that to define the binary output. So we chose an output threshold temperature of 0.375. So anything above that gets assumed to be an output of 1, and anything below gets assumed to be an output of 0. And if we choose that threshold, then our 0, 0 input maps to an output of 1, and all the other inputs with a temperature of less than 0.375 map to a binary output of 0. So this constitutes a working NOR gate built from convective fluid interactions. So the question is, can we wire these convective NOR gates up to make simple circuits? And one of the simplest circuits we can try and make, given that the NOR gate is universal, is we can try and make a binary half addition circuit. So this is the truth table for binary half addition. Basically, if the system has two inputs, then of course both outputs are set to 0. If you have a 1 on either of the two inputs, you have a sum of 1. And then if you're giving two binary on inputs, then of course it shifts to a +1 in the carry digit and a 0 to the sum digit. And it's possible to make binary half adders out of 5 NOR gates. So we tried to link our convective NOR gates up to make a binary half addition circuit, and that's shown here. So what you're seeing in these dotted lines is basically the thermal communication between the gates. And by thermal communication, I essentially just mean that we assume there's a conductive link between, for example, the output of the gate on the lower left to the first input of the gate on the top right. So we just allow conductive heat transfer from the output to that input, and we parameterize it, but with a value of 0.05. So what does that mean, 0.05? Well, basically, 0 would mean complete thermal resistance, i.e. No heat transfer across the line whatsoever. And 1 would imply perfect heat conductance, so no resistance whatsoever. The heat would flow directly across that thermal wire. We found that 0.05 was a good compromise to avoid sort of noise and transients and spurious information transfer. So what we can see here is we've got the two inputs to our binary half adder. The first input goes to the two inputs of the gate on the left and the first input of the gate in the center. And the second input goes to the two inputs of the gate on the right and the second input of the gate in the center. And then we have the various links there constituting a binary half adder circuit comprised of NOR gates. In the example that we're seeing here, both inputs are set to 0. So as we saw before with the convective NOR gate, with both inputs equal to 0, we have this 2 convection cell state, and that gives a high output. So that high output is sent to both of the downstream gates there. Both of those downstream gates have been flipped into the single convection cell state, and so they're both giving a low output, which is what we would expect for binary half addition. For the next input in the truth table, where we switch input B on, switching that input B on flips those two gates on the lower right and center to the single convection cell state. And so what that means is that the sum gate on the top left receives low inputs because it's getting input from that lower center gate and the upper right gate. And so we are still in that double convection cell state for the sum gate. So the output there is 1. But for the carry gate over there on the top right, that's receiving a single on input from the lower left gate. So it's flipped into the single convection cell state, giving that carry figure of 0. Moving on to input 1, 0, it's a similar logic basically. We have the two lower left gates in the single convection cell state outputting a relatively low heat value to their outputs. So the sum gate on the top left is receiving relatively low outputs. It is a little bit skewed in this case, so we do have a little bit of spurious heat transfer, but it is still in the double convection cell state. You can clearly see there are 2 convection cells and not just 1. But the carry gate over there on the top right has been flipped into the single convection cell state by that gate on the lower right there. And then finally, if we give a 1 signal to both inputs, then all 3 of those lower gates get flipped into the single convection cell state. And so that means that the carry gate in the top right receives 2 low inputs, so it stays in the 2 convection cell state and gives a high output. Whereas, and because that carry output is high, the sum gate on the left there receives 1 high input, and that flips it into the single convection cell state. So the sum output is 0. And just to show you what it looks like in practice, we see the 1-1 configuration here. See, it settles into a steady state pretty quickly. If I go back, see, we start with homogeneous initial conditions. See, there is a bit of distortion on this up on the carry gate there, but it's still in the 2 convection cell state. So in summary, our half addition circuit from convective NOR gates does exhibit the correct truth table, again, as long as we choose our thresholding at 0.375. So any temperature less than 0.375 is considered a binary output of 0. And anything above is considered a binary output of 1. So this half adder circuit does exhibit the correct truth table. But of course, as we saw earlier, it is tricky, and there are some distortions in the flow field. And the reality is that we really need a nice form of error correction on this convective computation system. And that's something that we were thinking about back then. So I'm open to any interesting suggestions for how we can do a clever sort of thermal error correction to basically just correct those little bits of distortion that we see sometimes as we go downstream into these circuits, because of course that distortion becomes pathological with bigger circuits. So to sort of take this to the next level and be able to compose really large circuits, we sort of need to fix that distortion with some kind of error correction. So thank you so much for your attention, and I'm very sorry again that I can't be there in person, but please feel free to reach out, and I look forward to seeing many of you in the near future at various conferences and events.